I always forget. Good morning or good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is Josh from Business Review, and I'll be your host today. It is our pleasure to have Smiths Interconnect with us today, who will be presenting this webinar entitled Understanding Which RF Filter Technology Works Best for Your Next Module Design. Today's guest speakers are Chris Horn, Mike Schweier, and Sean Adams. I'd like to welcome you to our webinar platform On24. You'll notice that this webinar is browser-based, so if you disconnect for any reason, please just click on the link that you received via email to rejoin the session. And in order to ask questions, you can send them in via the questions widget. Just type them into the box at the top left-hand corner of your screen and click Submit. We will allocate some time at the end of the session to address any questions or thoughts that you may have had. And please use the yellow Help widget if you require any assistance, and you can move, resize, and maximize any of the windows in front of you to get a better view of the slides. Please note in the resource widget you'll find today's presentation along with some additional helpful content to download. But for now, please allow me to hand over to Chris.
Thank you, Josh. We're excited to talk to you all. Today we'll be covering several important topics surrounding RF filter technology and ultimately discuss what key parameters you should consider when choosing the best RF filter solution for your next system design. We will start by discussing the various types of RF filter topologies currently available in the market and the key electrical and mechanical application parameters surrounding each of these products. We will focus on the most important characteristics such as frequency band, rejection, insertion loss, package size, and mounting style. This will give you a better understanding of how the optimal product design is realized and produced. To conclude, we will provide a valuable Smiths Interconnect perspective on how current and future market trends are driving the next generation of RF filter technology from both a design and manufacturing perspective. Today, we will be taking a look at the following RF filter topologies: discrete filters, also known as lumped element style filters, ceramic filters, cavity and waveguide filters, tunable filters, and planar X style filters. To start off, I would like to ask a survey question. You should see this on your screen now. What do you see as the single most important driving factor when you select an RF filter for your application? Is it frequency band, rejection, insertion loss, package style, or mounting style? We'll take roughly 30 seconds to gather your responses.
Well, the frequency band is what we expected, as the RF filters are very specific to many applications. It's good to know that that's basically what we're in alignment here.
Yeah, it doesn't come as a surprise, and we'll touch on each of the following filter topologies and explain which is best suitable for different frequency bands. Thanks for participating in the survey. At this point, I would like to pass it over to Mike Schweier, who will be spending some time discussing each of the important factors in more detail.
Thank you, Chris. There are many filter solutions available to support the wireless industry, depending on the application. These technologies provide trade-offs in performance, size and weight, and power handling, to name a few. The size restrictions to support personal cell phones versus the key performance for high-resolution radar would drive to a bulk acoustic resonator filter versus a cavity filter, for example. I'm going to highlight some of the key parameters for some of these solutions and provide the advantages and disadvantages for the technologies. The type of RF filtering that is required for the system is a key first point. RF filters can be designed for band pass, low pass, high pass, band reject or notch filtering, and multiple channel filtering or multiplexers. The ideal filter passes and or rejects signals in specific bands of interest. Two examples of filter technology are shown. The upper response is a bandpass filter using a discrete design technique, and the lower response is a low-pass filter, also designed with discrete components. I'll get into deeper detail of the design techniques in the next several slides. These are plots of two types of cavity filters. The top plot shows a cavity diplexer, which has very good channelizing for two frequency bands of interest. The bottom plot shows the typical performance available from a cavity bandpass filter. I'd like to point out that these responses are showing better rejection and improved insertion loss compared to the previous slide. So how does one choose the type of filter for each application? The frequency band of interest will provide a starting point into the type of filter solution available. The discrete topology supports filters in the DC to about 10 gigahertz range. These filters, also known as lumped element or chipped and wire filters, are essentially LC structures designed with specific poles and zeros to obtain the desired filter response. The advantages of these type of filters are the potential of small size, but the loss is limited mostly to the available inductor and capacitor Qs. Since these are designed with series and parallel resonant structures, the filter designs provide a lot of versatility as shown with the low pass and band pass results previously. The frequency limit is due to the size limitations of manufacturing such small inductors and capacitors. The more common applications are provided, which include transceiver requirements, up or down converters, SATCOM, and radar applications. Another topology comes into play for frequencies of 400 to 6,000 megahertz, which is a ceramic or dielectric resonator filter. These filters are typically provided in surface mount options and may be mass-produced to produce an economical solution. These filters use quarter wavelength dielectric resonators of various materials and sizes to provide the filter response. The drawback of this topology is their durability, especially at higher frequencies. Typical applications for these filters are military applications and UAVs, and also industrial applications such as wide area networks. For higher frequencies in the Ka band up to the millimeter frequencies, cavity and waveguide filters are applicable. These filters are low loss and have very high Q, but are larger and usually have higher costs. When low loss is the most critical parameter, these are the filters for the application. As with the other filters, the size decreases with increased frequency. These filters can also handle much higher power than the other topologies. These designs are precision machined with either quarter wavelength metal resonators for the cavity or waveguide resonators for the waveguide filters. The applications are similar for the other filter types, but the performance of the filter with the higher frequencies and/or power handling leads to overall improved system performance.
So Mike, with all the buzz surrounding today's 5G applications, do you see these products as a good solution for low-cost millimeter wave requirements?
That's a good question, Chris. There are certainly limitations with this approach for the commercial style applications, where other considerations come into play. We'll touch on another type of topology shortly, and that is the planar style filter that is more suited for high volume, lower cost applications where surface mount technology is key. There are also design techniques that are utilized in order to optimize certain aspects of a filter's response, and the theory is the same across all the filter options. Some examples include capacitively coupled nodal circuit design for narrowband use, mesh circuit design for steeper high-side rejection. As you can see from the equivalent circuits, the nodal design circuit utilizes capacitively coupled resonant circuits to design the narrowband filter. The dual or reciprocal design technique to the nodal is the mesh circuit design technique. It is easy to see the asymmetrical transition for each of these design techniques with the high or low side rejection. Additional techniques are available for designing more symmetrical filter responses. Other design techniques include elliptic designs for the steepest out-of-band attenuation and placing poles to suppress specific frequencies as shown on the left and right responses respectively. Additionally, cavity filters can employ comb line design techniques for narrowband responses or individual techniques for wideband results. Let me also point out a filter transition from passband to stopband is a function of a number of sections or poles within the design. Adding poles does increase the steepness of the transition, but at a trade-off of requiring a larger size and increased insertion loss across the passband. And there are other issues that would apply to the filter solution for a specific application, but besides just the required operating frequency. For example, passband ripple, ultimate stopband rejection, and group delay variation could lead to a specific filter type. Filters are available in integrated filter assemblies, or IFAs, such as a tunable filter as shown here. Tunable filters have several filter bands within one subsystem that can be tuned to change the bandpass or band reject frequency with either a manual or digital input. Other IFAs would include switch filter banks, which have switches, most commonly pin diode switches, to switch between bands. These solutions provide more capability, but again, with an increase of size. For many applications, overall size is often the most important critical parameter for the application. One solution for reduced size is the planar filter technique, and I will turn it back over to Chris to discuss in detail the attributes of these filters and their manufacturing techniques.
Thank you, Mike. Before we jump into the next style of filter, we would like to use this time to ask the audience another survey question. So what type of filter topology do you see most commonly used in your system applications? Is it discrete lumped element style filters, ceramic filters, cavity filters, or waveguide style filters?
Well, thank you for the responses. It seems like we've tied with 3 of them. I guess the cavity is the one that stands out with the least amount of responses. So yeah, it shows the great versatility of the advantages of each of the different filter types.
Thanks, Mike. So now we want to take a look at planar style RF filters. Looking at today's market trends, designers are looking for high performance, smaller size, easier to implement, as well as reduced costs in RF filters. This is where planar filter technology is key. Planar filters use a monolithic construction using a substrate of a given dielectric with added metallization. Filter circuits are easily produced on this type of design. Due to the wide variety of substrate options and design flexibility, these products provide RF performance that traditional filter topologies just can't compete with. This style of filter is much smaller than the traditional topologies and is ideal for surface mount pick-and-place applications. It can also be produced for chip and wire style applications. These products are also easier to produce in volumes and require little to no tuning, which provides a cost savings over comparable products in other topologies. The proven process technology is also suitable for high reliability applications in harsh environments, such as space, defense, and medical. Smiths Interconnect's line of planar filters are available to cover a wide range of application requirements. Currently, we're offering products up to roughly 30 gigahertz in frequency, and we are currently qualifying products to go beyond this range. We are currently offering 30 dB of rejection over 5% bandwidth. These style products have also been qualified up to 10 watts of CW power. Looking at the mechanical specification, you will see that these chip solutions can be offered in either a surface mount or wire bondable style package. The substrate and material options selected are based on individual application and market requirements. Shielding is also available if a requirement by the customer. As mentioned prior, planar filters use a substrate of a given dielectric and a thickness in which filter circuits can be produced on the surface using either thick film or thin film deposition techniques. Smiths Interconnect is capable of producing designs with both processes. However, the selection will depend on the application requirements. Thick film processing consists of using a screen printer and conductive inks that are applied using a squeegee and mask to produce the filter artwork on the surface of the wafer. The inks are then dried and fired in a furnace at a temperature of roughly 850 degrees C. The only limitation with this type of process is that smaller features are difficult to produce, limiting us to line widths and gaps of approximately 2 to 3 thousandths. This provides a very robust adhesion that is well suited for harsh environment operation. Thin film processing, on the other hand, is a very different process in which conductive materials are deposited in a vacuum chamber using a technique known as sputtering. There's a target of a given material placed inside that chamber that is bombarded by energetic ions, which causes an exchange of momentum. At this point, atoms of the target material are ejected, coating everything within the chamber. The wafer with the masked features is also present in the chamber, which produces the conductive features on the surface. With this type of processing, the masking prior to sputtering is critical and typically consists of a photolithography step, which allows for much finer features than discussed with our thick film process. In this type of process, we are typically able to hold tolerances closer to 5 mils on the features. Overall, there are several advantages to the planar style filter, but ultimately they check a lot of boxes in today's SWaP-C challenges present in the market. Additionally, they offer RF performance that other topologies just can't compete with. Due to the mechanical structure, they provide low insertion loss, high rejection, with a broader frequency bandwidth. If you're not using this style filter in your current design today, I would highly recommend exploring this for new applications. At this point, I would like to turn the presentation over to Sean Adams, who will be discussing the future trends in the filter market.
Thanks, Chris. A lot of good information on our Planar X series of filters. It's a really great technology we want to pass on to our customers. Now for a little change of pace, we want to delve into the current and future trends we think a successful RF filter business needs to have in place in the years ahead. In keeping with the theme of printed filters, we'll first discuss where we expect this technology to be in the coming years. As an example, the current slide shows a conventional printed filter at Ka band and how we typically simulate the circuit in HFSS. The use of printed filters in RF assemblies have been around for decades. However, engineers and manufacturing sites have been competing to further perfect this technology. That is no different than here at Smiths Interconnect, where we have laid out where we want to see our printed filter designs in the coming months and years ahead. There exists significant potential growth in printed filters with regards to dual mode technology. Traditionally, printed filters utilize 45-degree, 90-degree, or 180-degree resonators coupled to achieve the intended electrical response. However, with the proliferation of satellite communications, 5G, and radar, these filters must be miniaturized while maintaining a comparable performance to their predecessors. By using symmetrical resonators, like the ones you can currently see on your screens, we can split modes that would have otherwise been degenerate with perturbations at a 45-degree angle of 2 orthogonal modes, much like in circular waveguide structures, which we'll cover more extensively later. This allows us to manufacture filters nearly half the size of conventional printed filters. Among these shapes, but not limited to, are fractal resonators. These fractal resonators allow us to fit relatively large lengths of transmission line in a very small and compact space. By focusing on this technology, we'll be able to provide our customers competitive electrical responses in half the size of our competitors on nearly every application. You'll see one of the main themes throughout this webinar is the dilemma of miniaturizing electrical components while maintaining performance. And the ability to stack multiple microstrip filters is just one of these examples. Ignoring the fact that these quasi-assemblies come with the innate advantage of extensive space savings, when stacked, these filters become more reliable, repeatable, and most importantly, cheaper. We feel the best way to realize these advantages of stacking multiple printed filters is by utilizing LTCC, or low temperature co-fired ceramic technology. For those of you unfamiliar with this technology, it is mostly used in hybrid circuits, inductors, resistors, and capacitors. The typical process shown on the slide demonstrates the space-saving stacking filters can provide by allowing us to interconnect each layer seamlessly and at low cost. Our next topic takes us into the world of waveguide filters. To better understand where we're headed in terms of more complex structures and topologies of waveguide filters, one must have a background with the roles different transverse electric or TE modes, and transverse magnetic, or TM modes, play in waveguide filters. These terms simply describe the mode's propagation through the waveguide structure. Any single mode will have both an electric field and a magnetic field associated with it. It is how these modes oscillate in reference to their propagation through the waveguide that tells us whether it is a TE or TM mode. As shown on the slide, a TE mode has no electric field along the direction of propagation, and a TM mode has no magnetic field along the direction of propagation. The opposite is the case for the likes of a magnetic field for TE mode and the electric field for the TM mode. There are a number of TE and TM modes in a given structure, given it is designed correctly. They are referred to as TE or TM, MN, with the representations of M and N as integers indicating the certain mode that is in a waveguide structure. In the interest of time and the reality that you all may not be as enthralled with waveguide modes as I am, we'll focus on the TE modes and the role they play in dual mode filters. A typical dual mode filter is shown in this presentation, courtesy of the Mycium U-Wave Wizard software. There are almost a countless number of ways to do a dual mode or even triple mode waveguide filter. Today we'll focus on what we think will give us the best chance to deliver our customer exactly what they need in terms of the best possible solution in the shortest amount of time. Given the proliferation of satellite communications, we're focused on providing dual mode solutions in circular waveguide cavities at E-band and below. Conventional filters are subject to the disadvantage of having one mode or resonance in a given cavity. Using the circular waveguide approach, we can fit two modes or resonances in one cavity. We take degenerate orthogonal TE modes, excite them, then split them in the cavity to a given bandwidth. We then add one or more of these circular cavities with the two orthogonal modes and separate them with a plate containing one or more small windows. This allows us to achieve a high Q, narrow band solution with finite zeros and an extremely selective response. They also lend themselves to be cascaded with other similar filters at incrementally different frequencies to create a contiguous multiplexer for a wide array of applications. The same concept can be used in the case of dual mode diplexers, the only difference being two or more modes we excite in a separate frequency bands, thus create two separate bandpass filters. This allows us to fit two or more filters in the size it would take to do a single simplex filter. Similar to the advantages of a dual mode filter, dielectric field waveguides can greatly reduce the overall size of a waveguide structure. We'll stay in the most conventional realm of rectangular waveguides. These rectangular waveguides are most often filled with air. Sometimes they're even pressurized in applications that require higher power ratings. However, when the need becomes size as the number one priority, we can then introduce a dielectric. By filling a waveguide with something other than air, we start to see the benefits in significant size reduction of the overall part. Depending on the electrical response we're trying to achieve, we can either fill the cavity or strategically place dielectric along with air to create more selective responses. Utilizing low loss, high dielectric ceramic material, the overall product results in a much smaller footprint while maintaining most of the low loss properties inherent in waveguide technology. Of course, when we start to miniaturize our filters, acceptable dimensional tolerances miniaturize along with the part. On your screen, you'll see a printed waveguide hybrid Smiths engineers were able to successfully 3D print and plate. We've come a long way since the 1980s when the notion of 3D printing was first realized. Since then, we've seen major advancements in terms of materials and complexity of a finished 3D printed structure. Now, with the availability of printing in a plastic medium or even an aluminum alloy, we are able to realize highly intricate structures for RF filters. This allows for shapes and assembly improvements never before seen in the world of RF. With the ability to make complex structures, usually restricted to 3D software, we now have ways to make filters more efficient, easier to assemble, and immune to the limits of CNCs. Once the parts are finished, we can then plate in copper, silver, or even gold, and effectively achieve the same performance of a machine part.
So Sean, what type of products do you see additive manufacturing being useful in, and how could this approach to manufacturing affect our filter performance?
Good question, Chris. I can see waveguide or cavity filter structures as the most logical topologies to benefit from 3D printing. This would not only allow us to add features not possible in machine parts, but it could also reduce the touch time seen in manual tuning. Not only could we provide new structures with improved performance, they would be more repeatable due to the nature of the process.
Thanks, Sean. It is very exciting how this could change the approach to manufacturing. I know Smith has started some exploration on this front.
Sure, Chris. We've come a long way from just printing action figures. Areas that could greatly benefit from the precision of additive manufacturing are RF filters in the ranges of V and E band. As Earth's orbit becomes overcrowded with satellite communications, it behooves operators to fit more and more information in a given channel. This means bandwidth in V and E band must be taken advantage of. However, with these higher frequency bands come unique challenges. Every aspect of the part is more critical and must be optimized to ensure quality. On the slide, you'll see a typical rectangular waveguide bandpass filter at 80 gigahertz we've simulated on HFSS. Things just don't work at V and E band like they do at S band, and we're working to perfect this technology. Similar problems exist at Ka band, though work is underway to find extremely high Q devices employing the use of dielectric resonators. Dielectric resonators work by encompassing most of the fields in a low-loss dielectric rather than metal conductors that can be lossy due to material, poor machining, poor contacts, or the introduction of contaminants. The need for ultra-high Q structures in bands as high as Ka band have been in demand for as long as systems in this frequency range have been in place. However, due to the size and material restrictions, dielectric resonators used in this high frequency have been mostly out of reach. While working closely with our vendors, we have made great strides toward making these frequency restrictions a thing of the past. With the prevalence of highly reliable 3D simulation software, we are now able to experiment with different shapes, sizes, dielectric constants, and support structures. We have already experienced customer requests for low-loss, narrow-band filters that will need this technology, and we fully expect to support it. Due to customer demand of smaller and higher Q devices, there has also been a rush to market for high Q coaxial filters with small footprints that are able to be surface mountable like you see on the slide. Coaxial filters, unlike their printed brethren, are synonymous with low loss and higher power handling. Their ability to be miniaturized and soldered on next higher level PCBs will provide customers with the ability to lower power on transmitters and lower noise figure on their receivers without sacrificing space.
Thanks, Sean. At this time, we would like to use one final opportunity to poll the audience. Are there any of the following topics that Sean presented today that interest you the most when it comes to the future of RF filters? The options are dual mode filtering, dielectric filled waveguides, planar filters, additive manufacturing, or V and E band applications. So interesting enough, it looks like the majority of our responses are targeted around planar filters. As you can see today, Sean has presented some of the additions we're adding to our product line and what our future looks like. We're excited to expand this offering, and we'll be happy to answer any further questions at the end of the presentation today. So today we've covered several important topics surrounding RF filter technology. Mike started with a look at several different types of traditional filter topologies, and then we dove a little deeper into the advantages of planar filter technology. We touched on the important key parameters that should be considered when selecting a filter for your application, including frequency, rejection, insertion loss, package size, and mounting style. And Sean concluded with some of the highlights of what the future of RF filters look like in both terms of products and process technology. I wanted to take a moment to highlight a very useful tool that Smiths Interconnect offers on our website that can be extremely beneficial when selecting your next filter. The Filter Select Plus tool can be used to search through a wealth of existing filter designs with a few simple inputs. By providing a few basic mechanical and electrical requirements, the tool can search through the available options and provide a basic data sheet with RF performance plots. If you find yourself in need of an RF filter, I recommend spending a few moments with the tool to see if we have an existing option for your application. I also wanted to highlight that it does not stop there. If you do not find a perfect match, just let us know. We're always willing to work with you on your specific application needs. As you've seen in the presentation today, Smiths Interconnect is a leading expert in RF filter products. We offer full design services from electromagnetic simulation to rapid prototyping. Our products are suited for a wide range of high reliability applications, servicing the commercial, aerospace, and military markets. In addition, we are able to offer added value, high reliability testing, ensuring mission critical success. We are constantly pushing the boundaries of size, weight, and power without sacrificing RF performance. We currently offer our new line of planar filter solutions up to 30 gigahertz with optimized performance and package flexibility. Our line of ceramic resonator style filters are a great solution for applications up to 6 gigahertz, where cost effectiveness is a vital requirement. We have a wealth of different style discrete filters available up to 10 gigahertz that are easily customizable to suit individual application demands. If you're working up towards 40 gigahertz, our cavity style filters may be a better fit, and we have significant experience designing these high-performing style filters that are suitable for both high power and low loss. We even have a line of tunable filters that are suitable for lab use, providing the user a customizable bandwidth and analog or digitally controlled options. So as you can see, whether it comes to a standard style filter or a more complex custom solution, Smiths Interconnect has the design and manufacturing expertise to produce cutting-edge RF filters. This will conclude our presentation for today. I would like to thank everyone for attending and participating in today's presentation. I hope you were able to gather some valuable insight in the world of RF filters. We hope Smiths Interconnect can be of assistance in your next application, and we look forward to working with you in the future. At this time, we would like to open up questions and answers. Okay, we have several questions here today. To start it off, we have one question surrounding our typical lead times and how long does a typical development take on a new design. Mike, I would like to pass this one over to you.
Oh, sure, Chris. It really kind of depends on the complexity of the filter, or if it's a multiplexer, for example. But for core standard package designs, 6 to 8 weeks is what our development time. For more complex designs, it's roughly about 12 weeks.
Great, thanks, Mike. We have a question surrounding our simulation tools. What type of simulation tools do we currently use? Sean, I'd like to pass that one over to you.
Yeah, Chris. So normally we start out with a filter synthesis software we call Guided Wave or CMS, and then what we normally do is we find Q and number of sections, what kind of rejection we think we can get, and then we go to a 2D simulation software, AWR Microwave Office. From there, once we build up the circuit, we then take it to a 3D simulation software in HFSS, where we can use analytical derivatives to form mesh on different geometries so we can tune in real time. We can even put lump ports on the filters and actually tune the filters in AWR. So we mostly use CMS, AWR, Genesis actually as well, and HFSS.
Great, thanks, Sean. We have several questions surrounding planar filters, which is really not a surprise after our survey question today. The first question is, do we build planar filters to a spec? The answer to that is yes. We have both products that Smiths Interconnect can provide as standard, and then we also will work with you on a custom spec if required. So we also have a question, Sean, about the typical Q factor of a planar filter, roughly 20 to 30 gigahertz.
So we've actually done a couple filters at the 20 to 30 gigahertz range, so we actually have some good data at this range. We usually get about 250 to about 275 worth of Q right there.
Okay.
Depending on the material that we use, of course. We typically do it on barium titanate or maybe alumina, and we see Qs of 250.
So we also have some questions surrounding SAW and ball style filters. You want to address that one, Mike?
Certainly. I see a question here. What is good technology at 145 megahertz except SAW filters? Discrete is a very good response topology for that frequency range. Because it can be one of the smaller sizes and it would work very well for that kind of application. And another general question, I'm sorry, was discussions about SAWs in general. Just very quickly, SAWs are limited to about 2.6 gigahertz for the upper end, and that's just due to the line widths that are achievable with liftoff or even reactive ion etching. So, they're a lower cost kind of option for lower frequencies, but they're definitely limited to about 2.5 to 2.6 gigahertz.
Okay, thanks, Mike. We also have a question. What is the smallest S-band planar filter we're able to produce in terms of footprint?
So a lot of this kind of, yeah. So a lot of this kind of depends on how selective you need the filter to be, how many sections that we were going to put in it, if it needs, a low pass cascaded with it, if you want your spurious to be pushed out a little bit higher in frequency. But we've been mostly doing S-band filters around the 1-inch range. Of course, that'll get extended if you need a low pass filter in there as well. It also depends on kind of what material we use. But if you wanted it as small as we can do it, we'd go barium titanate, and we can get you around 1 inch.
Okay, we also have a question asking if we can do ITAR type products. The answer to that is yes. We'd be happy to work with you on that. Okay, so we have a question surrounding the status of our E and V band filters. I know we're working towards this on our roadmap items. I don't know if you want to address that one, Sean.
So yeah, we've actually had a couple of customers come to us about V and E band products. We do have V and E band capability even now in-house. So I mean, we absolutely would take requirements. But yeah, I mean, I guess it all depends on the requirement. We have analyzers in-house that we can do V and E band products on.
Okay. So we have another question asking what type of filter would we recommend for small size and good performance at Ka band? I think the planar style filter would be the best approach for this. We have produced a few samples in this range, so we'd be happy to provide some more information on those products. Okay, so we also have a question surrounding space qualification, and if this can be provided for military grade filters. You want to take that one, Mike?
Oh, sure. Yeah, so we have experience supporting some space programs, and it's something that Smiths is very strong with across all our product lines. So yeah, so we definitely can work with specific requirements of each customer with regards to space screening or qualification, and we can help guide also with what we would recommend based on the orbit and radiation levels.
Thanks, Mike. We have several questions today. If we're not able to answer your question, I would also recommend taking a look at the resource section currently available in the tool today. There's a wealth of information there if we have not addressed your specific question. So we also have a question surrounding barium titanate as a dielectric for planar filters. Are there any implications using the high K in terms of temperature stability? You want to take that one, Sean?
Yeah, yep. So we actually have done some filters in barium titanate in K-band that we've done full qual on, and they've been very, very temperature stable. It's kind of inherent in these ceramics that they just don't move frequency-wise. Obviously, when we get to higher temperatures, they deQ a bit. Colder temperatures, they increase in Q. But we'd be happy to send over test reports or anything like that you'd want to see from the barium titanate temperature stability, for sure.
Okay. We also have a question. Can Smiths offer DC through for active GPS antennas? You want to take that one, Mike?
Sure. Yeah. Absolutely is the easy answer there. There's some special considerations that we would have to do with the connections in order to support that, but we have the experience with that. Based on the frequency range for that, it would work, for example, with cavity filters, as one example, with bias T.
Okay. We also have a question surrounding, who is the point of contact for accessing a spec. We touched a little bit on the filter select tool. I recommend, taking a look at that first off for your application needs. There should be some information there too on who to contact in your individual region. We'd be happy to provide some more information to that as well. So we have a question asking, what is the usual max power rating for planar filters? Would you like to take that one, Sean?
Sure, yeah. So I think what we advertise is usually around, 1 watt. But that's just what we advertise. I think we could actually get the power rating, and we've done the qual reports before. They usually start to degrade around 50 watts average power. As long as you stay under 50 watts average power, I think we would be good.
Okay. We also have a question, what are the best suitable filters for lower frequencies, particularly L-band? Mike covered several different topologies that would be suitable for lower frequencies. Could go with a ceramic style approach, a discrete, maybe even a planar filter style. So we'd be happy to look at your individual application needs there. So there's a question further on the simulation side of things. How long does a typical simulation take? You want to answer that one, Sean?
Sure, yeah. So of course it all depends on geometries and how steep the skirts are, how selected the filter is, or even what we're simulating. But typically our simulation time is kind of iterative at the first stage. But once we get to certain points where we need to know what dimensional tolerances we'll do, sometimes that simulation time can take 4 hours, 5 hours, something we run parametric sweeps overnight even. So it could be as quick as, checking a loading on a filter, and that takes 30 seconds, to as long as overnight and it's still running when we come back in the morning. if we want to see more dimensional tolerance stack-ups and see whether we want to go a thick or thin film process, or even E-band waveguides if we need to know what kind of tolerances we have to hold while machining those as well.
Okay. So we have quite a few questions surrounding LTCC technology. I'm not sure, Sean, if you want to spend a few minutes kind of explaining that process again. I'll jump back a few slides to help.
Sure. I don't know if I have the expertise to spend a couple minutes on it, but I can speak to it for sure. LTCC will kind of allow us to be able to stack these printed filters. When it comes to the planar side of things, when we're talking planar, we mean microstrip filters. With these LTCC filters, we can actually build up these separate microstrip filters in stages or stacks, if you will, all at the same time. So it just allows us to interconnect each layer. They're already doing it with plenty of other applications. We just want to take it to stacked printed filters.
Okay, thanks. So I think we're able to address quite a few questions today. If there's a few that we weren't able to answer, we'll try to follow up with each of you individually today. Like I said, I think one good solution is take a look at the resource section provided today. But again, we thank everyone for attending today. Hope you were able to learn some valuable information regarding RF filters. If there's anything we can do to support your next application, please let us know.
Okay, thank you very much, Chris. Just a reminder to the attendees, you will receive an email shortly telling you how you can access the on-demand version of this webinar, or you can access this through the Smiths Interconnect website at www.smithsinterconnect.com, or our website, which is www.business-review-webinars.com. And we look forward to sharing further webinars with you, so please do keep an eye out on the website just mentioned. Thank you once again, and I hope you all have a nice day.